All right, well, we're getting near the end of the very first lecture that we've had in this course. And we'll close out by doing a little activity through the program R. So make sure you've done the introductory lecture material talking about how to get R set up and a little bit of the basics. In fact, a lot of this is just going to be review from that. But here we're going to talk about how do we do the t-test, the chi-squared, and the correlation. And we'll also dive into what by hand activities mean, because some of your program activities may, some of your homework programming activities may have you doing some of the problems quote unquote by hand, and we'll explain what we're looking for when we ask you to do that. So for the t-test, we're going to start with something called long data, and long is a format of data. So if you think about a t-test, we have two groups. Long data, we can look at this. I'm going to use the package BSDA, all caps. So if you haven't installed that package already, I'd undo the comment and go on and run this line to install that package, and then I'm going to use the achieve data set. So in the achieve data set, you'll see that the groups are not listed. It's not like a boys column and a girls column, and then the scores are the data points in each column. You'll see that there's an outcome column, a dependent variable column, and a input column, an independent variable column that has the groups listed as entries in the column. So this is a long data format, and then the wide data format would have like a boys column with all the scores in it and a girls column with all the scores in it. Though this is a bit of a weird description when we've only got two variables, I think you can see how those would explode if, say, we had 10 variables. So let's say we had scores for the different political parties. So let's say we had, Republican, Democrat, and I think the marijuana party is what we used. But let's say we had Libertarian and Progressive and a whole bunch of other ones. So if we did it this way, we would have political party, and then you'd list out whatever political party you are in that column, and then your score. And you can see how this would get very, very long, because as we add political parties, we don't add any columns in the width, but we do add more and more rows in the table. Vice versa, if let's say we were doing political party and wanted to make wide data, if we had Democrat and Republican and marijuana party, we'd have 3 columns, but as we added Libertarian, we'd now have 4 columns, and if we added Progressive, we'd now add 5 columns, and Anarchist, we'd now have 6 columns. So as we add information or add more groups, our data becomes wider and wider and wider, and that's where the names long data and wide data come from. Now for the t-test, specifically the function in R is t.test. And with that t-test function, we can handle both long and wide data. So to handle long data, first I'm going to do a box plot of the data just to see what it looks like. So I'm going to use the dependent variable, then a squiggle, then the independent variable to tell R to make box plots of the dependent variable, the outcome score, broken down by this variable gender. And then I'm going to tell it to use the data set achieve that I assigned here, where I just told it to use the achieve data set from BSDA and call it achieve. So I'm going to do the same notation with t-test as I did with box plot. I'm going to take the dependent variable, squiggle, independent variable. This is the formula notation, and you'll see this used in other functions in R. And what I see is that I get a t statistic, I get a weird number of degrees of freedom, then I get a p-value. And then you also see I get a mean estimate in the girls group and a mean estimate in the boys group. So I will just pause quickly and say that the degrees of freedom are indicated from the fact that we're using a Welch's correction, which is a correction if we had unequal variances in each of the groups. We can turn this off with the t-test by setting correct to be false, and then we see that, oh, that didn't work. Uh-oh. So see, now I can't remember, but this is great because this is actually exactly what I do when I get a command wrong. is I do question mark and then the command and go look in the documentation. So as we showed in the intro videos, this is how we check documentation. Here I see, looking in the default methods, that it's not correct. It's actually var.equals equals false. So what I type instead of correct being false is var.equal equals false. And actually I want var equal to be true. So var equal equals false is its default method. That's what it's saying here. Default to var equals being false. But now if I type var equals being true, this is going to be my traditional two-sample t-test. So if I'm comparing to something I would calculate by hand, this is what I would want, is the var equal being true, because our by hand method didn't include the Welch's correction for the degrees of freedom in the t-test. So var equal equals true is how I would double check something by hand. And again, I can go and look at this information if I want to. I'll do it if I want to find some details about the different options that I could do. So I could do paired t-testing and different alternatives, etc. Note that here the term formula, that's what we're using when we use the squiggle, is formula. So that's something that you can see in there as well, and that's what that means. You can see I get a confidence interval, I get a whole ton of information, but the big things that I would look at are the p-value and the mean value in group for the boys and the mean value in group for the girls to see, okay, well, which one is higher, and we can see that the girls is higher. Of course, this is also why I use a box plot or a graphical method to give me an idea of what that would look like. So if I found a statistically significant result, girls would be higher than boys. Note that if I use the correction versus not using the correction, this gives me a very different conclusion statistically. But even if I found a quote-unquote statistically significant relationship here, the confidence interval, though it doesn't contain 0, is very, very close to 0. And this is why the confidence interval is so important. Is, yeah, you found a statistically significant relationship, good for you. But this confidence interval is pretty close to 0. So 0 is not a completely unreasonable value here, even though it's not quite at the 0.05 level of reasonableness. So for wide data, we can just take this and reformat it. So we have a vector of boys scores and a vector of girl scores. And how I would feed it into the t-test function is t-test and then boys, or whatever my first vector is of the first group, and then the girls the second vector in the second group. I can see this here where I'm going to write the var equals true again, and that's going to give me the same results as above with the same p-values and everything like that. So I have a little note here just for us to read through. Note that it's the same answer whether we use long or wide format. All that changes is how we type it into the function. And which one we use really just depends on how our data comes. So if my data come in a long format, then I'm just going to use this format to type it in. If they come in a wide format, then I'll use this one. Of course, you can always transfer between the formats if you really want to, and here's an example of how we did that for a couple different variables. So more information on the specific function, as we checked in this video, can be found by using the documented details using the question mark key to find those documented details for any function that you know the name of. All right, now for chi-squared. So in the chi-squared, I'm going to go on and make a table, and I guess I'll just go on and show what this table looks like, ability _ tab. So this is the ability of individuals, girls and boys. Are they hopeless, below average, average, above average, and superior? I think this hopeless classification is just hilarious. But there it is. So we can do the chi-squared test. And the chi-square test is just going to automatically calculate that. It takes a lot of that work of finding the expected values, and doing the subtraction takes that all away for us. So we have our chi-square statistic, the degrees of freedom, and then the p-value of that test. So very, very simple output here for the chi-square test. I will note that sometimes it's nice to mentally double check the degrees of freedom. So degrees of freedom are 4. Let's see if that makes sense. Well, we have rows minus 1. So I have 2 rows, minus 1 is 1. And 1, 2, 3, 4, 5 columns, minus 1 is 4. So I take 1 times 4, and that gives me 4 degrees of freedom. So that does make sense. If you don't remember where I'm getting these numbers from, go back and check your notes. Now, all of these tests have some interesting side features, but we can explore this in the chi-squared because we discussed that it's kind of tough to talk about effect size. So I'm going to go on and save the chi-squared test as ability underscore chi-squared underscore test, and then call a couple of components from it. So first I'm going to call the observed values. This, as you can see, is just the table that I gave the test. Then I'm going to call expected. So this is what is mathematically expected if the categories were truly independent. If the ability was truly independent of gender, this is what we would expect. So what we can see in comparing the observed to the expected is, well, we have a few more hopeless girls than we would have expected by random chance. We have a few more below average girls than we would have expected by random chance. We have a few less average girls than we would have expected by random chance. We have a few less above average girls than we would have expected by random chance. And we have a few less superior girls than we would have expected by random chance. So though we don't actually have a claim as to are girls better than boys or anything like that, that's not what we're testing. We're just testing are these independent or not. Doing an interpretation, it actually seems like girls are performing less than we would have expected than by chance. Now, what you'll note is that when we just have 2 categories, if one of the categories is performing less, one of the categories will be performing better. Now, this is the case because of the way that this problem is set up. For every problem, you need to interpret it differently, but you can see that comparing observed versus expected is how I'm running this interpretation. So let's look at this. For boys, boys also have, boys have less hopeless observed than we would have expected by chance. Boys have 35 hopeless students, and we would have expected by chance 45. They have less below average than we would have expected by chance. They have more average than we would have expected by chance. They have more above average than we would have expected by chance, and more superior than we would have expected by chance. So for this sample, we have a statistically significant evidence that there's a relationship between ability and gender. And then after looking at the breakdown between expected and observed, it appears that boys are performing more than we would have expected if these, better than we would have expected if gender and ability were truly unrelated. Now, there's also this thing called residuals, which is a relationship between this observed and expected value. So it's not just the difference between observed and expected. We're doing a little bit more to it than that. But what you'll see is that when the observed is higher than the expected, the residual is positive. And when the observed is lower than the expected, the residual is negative. So we have fewer boys that are hopeless, fewer boys that are below average, more boys that are average, more boys that are above average, and more boys that are superior. And the places that we're seeing the largest relative gain is in the above average category. So note that it's not just, is this, this looks like it's about 11 different, and that might not be the largest raw number difference, but in terms of a relative difference, this is the largest relative difference in the category. So that's important because this is more standardized and lets you highlight, okay, this is actually the category where boys are most doing better than girls in a bigger way than any of the other categories, is that they're above average in this way. And same thing down here, the girls in the hopeless category, this seems to be the biggest one where there's a larger discrepancy between girls and boys relative to the numbers that are in each of the categories. So we mentioned that effect sizes, not necessarily as straightforward for chi-squareds, but this is a way in which we look at the size of the effects and where these effects are differing. The ability is an ordinal variable, and again, it lets us make ordered claims here as we're going up and beyond. It's not always the case with the chi-squared, but it is always the case that by looking at the observed and the expected or the residuals, that we can identify the locations of cells that have the biggest differences between what was observed and what would have been expected by random chance. All right, so last but not least, let's discuss correlation. And I'm going to show you what we mean when we say by hand in R. So all that I mean when I tend to say by hand is that I don't want you to use the built-in function. So for instance, first thing we're going to do is calculate the correlation by hand. I'm going to use the sepal length and sepal width from the IRIS dataset. Now, the correlation coefficient had a numerator and a denominator that were kind of these long, nasty equations. So I just broke them up into sub-equations just so that the code wasn't too overwhelming, though, you know, this is still plenty confusing, and it's important to make sure that you're getting your parentheses right, especially on this one where you want to do the squaring inside of the sum. It's important to make sure that your parentheses are in the right place. So in any case, I have the numerator and the denominator, so I'm going to calculate those. And then I'm going to do my correlation coefficient. Now, note that this counts as by hand. And again, when I say by hand, all I'm meaning is if I ask you to do a correlation, don't do the correlation function. Actually show me that you can calculate, give me the underlying code of how that correlation function's calculated. And I don't mean give me the actual underlying code. I'm just trying to say I want to see you do this on your own as if there weren't a correlation function to demonstrate that you can and that you understand the principles well enough to put this together yourself. So we can always check this, and if you do it by hand, not only are you allowed to check it using the built-in function, I highly recommend that you check it using the built-in function. So we have this correlation that you can check, and hey, using the built-in function, we see that it's the same, that our built-in function matches our by hand calculation, and this is what you want. Now, if I'm doing a homework assignment and this didn't happen, well, then I'd want to redo it. Probably redo my by hand work, though if I'm still getting the hang of how to use the built-in function, maybe I'd want to double check that I'm using that correctly. But if I'm pretty sure that I'm using the built-in function correctly, then I'm going to want to double and triple check my by hand work to make sure that it's matching. One thing that sometimes happens is, like with the t-test, you saw that there's a correction. Sometimes if you run the correlation, or it's not a correlation, but if you ran a formula that wasn't a correlation like the t-test and you saw it's using some kind of a correction, then you may just want to fix that correction, and that's going to be what makes your handwork match what's output. So pay attention to that, especially if you're double checking handwork with output. But when there's a discrepancy, I highly recommend double checking and make sure you work on it until you get rid of the discrepancy so that you're getting all of your stuff right. All right, so how do we do the t statistic by hand? Well, I need the alpha for my eventual comparison, and then I also need the sample size to calculate t. To calculate t by hand, it's just the correlation times the square root of n minus 2 divided by the square root of 1 minus r squared. So I literally take the formula that I saw in my notes and I type it in with the appropriate parentheses, and that's how I calculate my t statistic. In this case, t is going to be negative 1.44. So for the critical value approach, I'm going to calculate my different critical values. Note that in this case, I'm using C, which is concatenate, and I'm putting together the lower alpha, alpha over 2, and the upper alpha, 1 minus alpha over 2, to get both the lower and the upper cutoffs. Of course, if you wanted to do this, and you just wanted to do a one-tailed test for the lower cutoff, you wouldn't type C, all this stuff. You would literally just put in alpha over 2 without any of the C or anything like that. So it'd be QT, open parentheses, alpha over 2, comma, DF equals n minus 2. I think I have it here, actually. And if I just wanted to use the upper cutoff, then I would use just the 1 minus alpha over 2. And actually, if I were doing just a one-tailed test, it wouldn't even be over 2 because I wouldn't have to cut my alpha in half. So it would actually, if I were looking at one tail, and this is incorrect, this would be QT alpha comma df n minus 2, not alpha over 2. So let's see, where was I here? Okay, so we did our alpha and we calculated our t. So looking at our t, I can see t is, so this is what separates the critical region. If I'm smaller than negative 1.97 or larger than 1.97, that's the critical region. 1.44, negative 1.44 is not smaller than that, so it's not in the critical region. And because of that, we fail to reject the null hypothesis. So there's not enough evidence to determine a difference. So to calculate a p-value for this, we use the pt instead of the qt for the p-value. And we give it our test statistic and our degrees of freedom. Now note that for a two-tailed p-value, I need to multiply that probability by 2. So this finds the probability of t. In this case, by default, it does lower tail, so the probability of being smaller than t. So on a graphic, we've got our t down here, and we're looking at the area to the left. But then I multiply it by 2 because we want as or more extreme in either direction, on the positive side or the negative side. And so for a symmetric distribution, that's just doubling the distance. Now we can check this with a built-in function. So I can check my t statistic, negative 1.44. That looks right on, negative 1.44. Degrees of freedom, I didn't really make a note of, but it's n minus 2. I can check that real quick. N minus 2 is 148, so that matches right on. And the p-value that I just calculated, negative 1.5198 and negative 1.519. So actually we're more precise than the p-value that's provided, but correct to the degree to which it's rounded in the built-in function output. I can also check the correlation, negative 0.117, negative 0.117. So what I calculated by hand, of course, we already checked that with the built-in system. So for graphics, for interpreting a correlation, typically we'd look at a scatter plot. Of course, you're going to give me much nicer scatter plots than what I'm showing you here, editing the titles and the x-axis and the y-axis and giving it a nice title and stuff like that. We're just showing you how to do this real quick. And then the AB line with the function notation, y, the dependent variable, x, the independent variable. So y squiggle x is how that would go if you're putting together a line. And then that adds the line, and we can see that there's a slight negative relationship, and in this case it's not statistically significant. So we don't even have evidence that there's any relationship at all. We don't have evidence that this line in the population isn't just flat. So again, in our sample we see that it's slightly down, and that's true, and nothing's going to take that away. But in the population, we don't have any evidence, or we don't have enough evidence to determine that it is a downward slope. So if we had a kind of a range of values that the population could be, it could very well be an upward slope, not a downward slope. And that's why we say non-significant. And we don't really go into detail. We don't say we had a slightly negative relationship if it's non-significant. We just say it's non-significant because in the population, we don't know that it is a slight negative relationship. We just know that for our sample. So this has been a quick intro to R and how we do some of the stuff that we talked about in our review slides, specifically going through how do we conduct a t-test in R using long and wide format data, how do we run the chi-squared, and then how do we do a correlation, both working by hand in R, which is something that you may be expected to do in a homework assignment, is do some of these by hand, maybe a correlation, maybe a t-test, maybe a chi-squared, doing one of those by hand, and how to use the built-in functions in R to do these calculations.